In the last video, we looked at an important theorem about quotient rings. We had three parts there. One is that image of a ring homomorphism is a subring, which was fairly easy. Second part was called the first isomorphism theorem, which says that if you have a ring homomorphism from R to S, it is an onto homomorphism, then R mod kernel phi is isomorphic to S. And the third part of the theorem was we had a bijective correspondence between ideals in the ring R that contain the kernel and ideals in the ring S. Okay. So, I want to do some examples in this video to illustrate the application of the previous theorem. Let me start with the example that I did a few videos ago about R mod x. So, if you have, so recall, I have showed in an earlier video that there is an isomorphism between these two rings. Okay. So, let me reprove that today, and as I said, this is an important isomorphism. If you understand this isomorphism, you really have understood important things about ring theory. So, this is something that you have to carefully think about and understand. But in order to prove this in a different way, so I am going to use an exercise which I mentioned earlier, but I have not solved this, but the solution is exactly similar to another theorem that I have done earlier. So, let K be a field. Remember, a field is a ring where every non-zero element is a unit, in other words it has a multiplicative inverse. So, then every ideal in, and let us consider, let I be an ideal of k x. Remember, k x always stands for the polynomial ring over k in one variable. So, I is an ideal of k x. Then there exists, so then there exists a monic polynomial f x in k x. Remember, what is monic? Monic simply means that its leading coefficient is 1. So, if it is a polynomial of degree 10, that means x power 10 is the largest power of x that you see there, the coefficient of x power 10 is 1. There exists a monic polynomial f x such that I is equal to the ideal generated by f x. So, this notation I have used before. This simply means that, this means in the ring of integers we know what this means. This because there it was, if you put brackets around 2, that means it is the ideal generated by 2, that means every element of that set is a multiple of 2. It is the same thing here. This means every element of I is a multiple of f x. That means it is of the form g x times f x, where g x is an arbitrary element of k x, right. So, an ideal generated by a single element is by definition that element times any ring element. So, why is this? So, this is exactly like the statement I proved, every ideal in Z, the ring of integers, is of the form n z or n, in other words, for some non-negative integer. Right. Remember this, I have proved this in some video, in a video a few videos ago. Here the key idea was division algorithm. So, division. So, we started with an ideal. If it is the 0 ideal, it is already of the form 0 times z. If it is not the 0 ideal, it must contain some non-zero number, then it must contain a positive integer, because ideal is closed under taking inverses. So, if it contains non-zero elements, it contains positive elements, and then we simply take the least positive element of I, and then we use division algorithm to argue that everything is a multiple of that, because we can divide by this least element, the remainder is a number strictly less than this element. So, it cannot be there if it is positive. So, it must be 0, in other words remainder is 0. The same proof works in Kx because we can divide polynomials also, just like we can divide integers. Remember though that to divide polynomials, to divide by a polynomial f, we need that the leading coefficient of f must be a unit, but in a field every non-zero element is a unit and leading coefficient is by definition non-zero. So, we can always divide by any polynomial, any non-zero polynomial. If f is a non-zero polynomial, we can divide by that polynomial in a field, in a polynomial ring over a field. So, that is why we can't divide in general in R x, and we do not have such a statement for R x where R is an arbitrary ring. This is only for true if K is a field. In other words, if K is just a ring, this is not true, okay, as we will do in examples later. So, in other words, we want to show that there is something. So, what would be the analog of least positive element? What you do is, if the ideal in Kx is not 0, so I will not do this, I will leave it for you to do because it is exactly similar. You take an ideal, if it is 0 you are done because it is generated by the 0 polynomial. If it is not 0, take the polynomial, non-zero polynomial which has the least degree. In other words, in fact take the monic polynomial with the least degree and then divide by it, argue that remainder must be 0. Okay. So, let me not say anything more about this, we will in a future problem session I will try to do this in detail. So, I am going to use this. So, in particular in R x, if R is the field of real numbers, every ideal is generated by a single element. So, let us apply this. So, consider the ring homomorphism. So, I am going to reprove the statement that we proved in a previous video. So, consider the ring homomorphism from R x to C, which takes f x to f I. So, I as always is a square root of -1, so imaginary number. So, what is this function? F x goes to f I. This is a ring homomorphism, is an easy check. In fact, I think I may discuss such examples when I define ring homomorphism. So, this is a ring homomorphism, I will not do this in detail. So, this is a ring homomorphism, let us assume that. What we are doing is take a polynomial with real coefficients and you evaluate it at the imaginary number I. So, you plug in x equal to I, you then get a complex number. So, it is an element of C. So, this is a ring homomorphism. What is the kernel of this? What is kernel of phi? So, that is what the question is. Kernel phi is all elements in the polynomial ring R x. So, this is f x in R x such that f of I is 0. Okay. So, now I know a few things. I know because of the fact or rather the exercise that I mentioned here, every ideal in kernel phi is every ideal in the polynomial ring R x is generated by a single element. So, by the exercise above, there is a monic polynomial f of x in R x such that kernel phi is the ideal generated by f of x. So, in order to determine kernel phi, I just need to find out f of x. Let us search for f of x. So, what are some elements of the kernel? Certainly, you know that by definition of I, x squared plus 1 is in the kernel, right. This is because I squared plus 1 is 0. So, if you take x squared plus 1 and substitute x equal to I, it becomes 0. So, x squared plus 1 is in the kernel. So, that already means that if f is the generator of the kernel, f x, so in other words f x times gx is x squared plus 1 for some, remember this is the definition of the ideal generated by f x. Every element of the ideal is a multiple of f of x. X squared plus 1 is an element of the kernel, so it must be a multiple of f of x. This already means, because this is degree 2, so degree of f is 0 or 1 or 2. Okay. That means, because if you have a polynomial that divides a polynomial of degree 2, its degree must be less than or equal to that, right, because degree of the product is the sum of the degrees. Degree of x plus degree of g of x is 2, so degree of f x is 0, 1 or 2. So now let us look at the possibilities. Can degree of f x be 0? Remember what is the meaning of this? Degree of f x is 0 means f x is a constant. But then what is phi of f of x? So f x is a constant, let us call it a in R, right. It is a degree 0 polynomial means it is a constant a, but then this is just a, but because if there is no meaning to substitute for x in a constant polynomial, under the function phi, a constant simply goes to the constant itself. Okay. So there is, in other words, a goes to a, but because phi is the generator of the kernel, in particular phi is in the f is generator of kernel and in particular f is in the kernel, phi of f is 0, that means a is 0, that means f is 0. But now this is a problem, right, because if f is 0, how can x squared plus 1 be a multiple of 0? X squared plus 1 then can't be a multiple of 0. x squared plus 1 can't be a multiple of 0, right, because obviously any multiple of 0 is 0. So in other words, 0 is not a possible degree for f of x. Okay. So the proof hopefully is clear. So f x can't be degree 0. Now let us see, degree of f x is 1, can this be possible? Remember f is a monic polynomial by choice. There is a monic polynomial f x such that kernel phi is all multiples of f x. So if f x is monic, that means f x is degree 1 and monic means f x is of the form x minus a. What are degree 1 polynomials? The highest degree of x is 1, so x plus x minus a or x plus a. In general you can have a coefficient, but because it is monic, coefficient is 1. But then remember f x is in the kernel as I mentioned earlier. So this implies x minus a is in the kernel, but that means I minus a is in the kernel. So I minus a is equal to 0, right, because x minus a under phi maps to I minus a, but that means I equal to a, but this is also absurd, right. Why is it absurd? This is absurd because a is a real number, imaginary number I is not a real number. So a real number cannot be equal to I. So 1 is also not a possibility. So degree of x must, f x must be, so degree of f x must be, but that means f x is equal to x squared plus 2, x squared plus 1, but then degree f x is equal to this because both are monic. It is a degree 2 polynomial that divides x squared plus 1, that means it must be x squared plus 1 times a constant. Remember degree of f plus degree of g here is 2. So degree of f is 0 means degree of g is 2, degree of f is 1 means degree of g is 1, degree of f is 2 is what we just established, that means degree of g is 0, that means g is a constant, but f is a monic polynomial, x squared plus 1 is a monic polynomial, so gx must be 1. Okay. So f x is x squared plus 1, that means kernel of phi is precisely x squared plus 1. So, now first isomorphism theorem says what does it say? Precisely that R x mod okay. So, I will write this down, but there is one additional fact to be verified. So, first isomorphism theorem says from the previous video, if you have a ring homomorphism R to S, R mod kernel phi is isomorphic to S. However, remember this must be onto. Okay. So, in our situation we have R x to C, we have this, we have kernel of phi is x squared plus 1. So, R x mod the kernel is isomorphic to the image. So, it remains to check, in other words. So, I can't yet say this, right. I have to check phi is onto, but I claim that that is trivial, because if okay. So, let me first say that if phi is onto, we have this. The missing piece here is that phi is onto. If phi is onto, we have this because of the first isomorphism theorem. But why is phi is onto? Why is phi onto? So, let us take an arbitrary element of the complex numbers a plus ib. Then remember that means a b are real numbers. Then phi of a plus x b is a plus ib, right, because remember a plus x b is a polynomial in R x, because a b are real numbers, and its image is obtained by plugging in x equal to I. When you do that, you just get x a plus ib. So, phi is onto. So, phi is onto R x to C, the map phi from R x to C is onto, its kernel is x squared plus 1. So, we conclude R x mod x squared plus 1 is C. So, this is another proof of this important isomorphism of rings that I did in an earlier video. Okay. But now it uses the first isomorphism theorem. Now, that is one application of the first isomorphism theorem. Let us apply the last part of the theorem from last video. So, let us now apply what the correspondence theorem says. Let us see what the correspondence theorem says. Correspondence theorem says. So, we have R x to C, which is phi. We have already established R x mod x squared plus 1 is isomorphic to C. So, this is done. Now, what does the correspondence theorem say? It says that the ideals in R x containing kernel phi are in bijective correspondence with ideals in C. So, let us write it down. Ideals in R x containing x squared plus 1 are in bijective correspondence with ideals of okay. So, now this is what the correspondence theorem says, but what are ideals of C? There are exactly two ideals, right. So, remember C is a field, any field has exactly two ideals. So, namely the 0 ideal and C. So, there are only two ideals here. So, we can conclude the only ideals in R x that contain x squared plus 1 are, there are only two ideals, because this set has two elements. By the bijection between this set and this set has two elements, right. And what is this set? Ideals in R x containing x squared plus 1. So, there are only two ideals containing x squared plus 1, and there are two obvious ideals that contain x squared plus 1, right, x squared plus 1 itself and R x. There is no other ideal. So, this is the point I want to emphasize. So, in other words, if you have an ideal x squared plus 1, x squared plus 1 is contained in an ideal I, which is an ideal of R x, that means I is x squared plus 1 or I is R x. There are no ideals between I x squared plus 1 and R x that are different from both of them. So, such ideals are called maximal ideal. So, x squared plus 1 is a maximal ideal. So, I will define this formally later, but this is just to give you a preview of this. This is called a maximal ideal, which maximal ideals are ideals which have this property, that there are no ideals that contain that ideal other than that ideal itself and the full ring. Okay. So, now this is a useful result using the correspondence theorem. So, now I want to do some more examples. These examples also are supposed to help you with understanding ring homomorphisms and kernels of ring homomorphisms. Okay. So, let us do the following. So, this is another example. So, actually let us just do one example which talks about correspondence theorem. So, the question is, determine the ideals of the ring C t by t squared plus 1, C t divided by t squared plus 1. Okay. So, now this is sort of application of the bijective correspondence theorem, but I want to set it up properly. So, let us call this ring R. We do not know what this ring is. I am not interested in knowing what this ring is. In fact, I do not even know what it means to know this ring. The question is only to determine the ideals of this ring. Okay. So, remember, correspondence theorem says that if you have a ring homomorphism, this already leads to an isomorphism of rings, quotient ring and the codomain ring, and then there is a correspondence of ideals in these two rings. So, here consider the ring homomorphism. Here R is already given as a quotient ring. So, I can define the following ring homomorphism from C t to R. What is R? R is C t modulo t squared plus 1. And what is this function? I will simply send it to f of t to I will send it to f of t bar. Remember, t bar is the t bar always represents the coset corresponding to t. In general, bar is a convenient notation to denote cosets in a quotient ring. So, I will take an element polynomial in t, I will simply replace t by t bar, all the other things are left as they are. So, this is an element of R. By definition, okay, so this is an exercise, phi is on 2, this is clear because t bar is in image, because t goes to t bar, anything here is a polynomial in t bar. So, it is in the image, and kernel phi is precisely t squared plus 1. See, this is exactly how we make R a isomorphic to C t mod t squared plus 1. So, this I will leave for you to check. So, this is easy, this is an exercise, this is also an exercise, but it is an easy exercise. This is slightly more work, but again use the fact that every element, every ideal in C t is generated by a single element, because C is a field. T squared plus 1 is in the kernel of this, because t squared plus 1 goes to t bar squared plus 1, but t bar squared plus 1 is 0. Okay. So, t squared plus 1 is in the kernel, and you argue that there is no linear polynomial in the kernel. So, this is as in the last example. Okay. So, this I will leave for you to do. So, now the conclusion of the correspondence theorem says that correspondence theorem gives ideals of R, which is what we are interested in finding, are in bijective correspondence with ideals of C t that contain t squared plus 1, right. The correspondence theorem, because C t mod t squared plus 1 is the ideals of C t mod t squared plus 1 are ideals of C t that contain t squared plus 1. So, in order to determine ideals of R, I need to determine what are the ideals of C t that contain t squared plus 1. So, let us do that now. So, let I be an ideal of R C t containing t squared plus 1. See, first of all, note that there are two obvious ideals that contain t squared plus 1, t squared plus 1 itself and C t itself. So, these are two ideals. Are there any more? By the exercise above, because C is a field, I is actually the ideal generated by f t for some t, some f t rather, some f t in C t. But t squared plus 1 is contained in I. This means t squared plus 1 can be written as f of t times g of t for some g of t in C t. Okay. Now, f t divides t squared plus 1. What are the polynomials that divide t squared plus 1? So, we want to find polynomials f t that divide t squared plus 1. Okay. So, now if you think about this, there are 4 such polynomials. So, certainly 1 divides it, right, 1 times f t squared plus 1 is t squared plus 1. So, that is one possibility for f. I will write all the possibilities here. The second possibility is of course t squared plus 1. T squared plus 1 itself divides t squared plus 1. These correspond to, here the ideal generated by 1, in other words, is C t. So, here f equals 1, here f equals t squared plus 1. So, the ideal generated by t squared plus 1 is of course the ideal generated by t squared plus 1. This contains t squared plus 1, this of course contains t squared plus 1. So, these are the obvious two ideals that contain t squared plus 1. Now, are there any other f's that divide it? Of course, there are, for example, t plus I. So, here t plus I times t minus I is t squared plus 1. So, in other words, the ideal generated by t plus I contains t squared plus 1. Similarly, the ideal generated by t minus I contains t squared plus 1. So, there are 4 ideals that contain t squared plus 1. And hence, there are 4 ideals in R. And what are they? They are 0 ideal. This corresponds to, so I will write down these and then I will tell you how to, what are the corresponding ideals in C t. Of course, there is R and there is t bar minus I and t bar plus I. So, these are ideals in R. What are the corresponding ideals in C t? This corresponds to the 0, this corresponds to the ideal t squared plus 1, sorry, this is not bracket, this is the ideal generated by t squared plus 1. So, this corresponds to ideal generated by t squared plus 1. This is the smallest ideal that corresponds to, that contains t squared plus 1, which is the kernel of the map phi. So, the smallest ideal in this set of ideals that contain t squared plus 1 is t squared plus 1 and it corresponds to the smallest ideal of R, which is the 0 ideal, and the largest ideal that contains t squared plus 1 is C t itself and that corresponds to the largest ideal of R. The ideal in C t that is generated by t minus I corresponds to t bar minus I. the ideal t plus I corresponds to t bar plus I. Okay. So, R has 4 ideals. So, R is a infinite ring, of course, R has infinitely many elements, but it has 4 ideals. So, this is again an application of bijective correspondence result. In order to understand ideals in that ring R, namely Ct mod t squared plus 1, we have used bijective correspondence and our knowledge about ideals in Ct to conclude that R has exactly 4 ideals. Okay. So, hopefully these examples and problems gave you some idea of how to work with rings and quotient rings and ideals. So, I am going to stop the video here. In the next video, we will continue our study of quotient rings and I will give a few more examples. Thank you.